In this video, we will cover integrated rate laws. I will show you how they are derived, though you do not need to be able to do the derivation yourself, and I'll show you how we can use graphs of concentration versus time and our integrated rate laws to figure out what the order of a reaction is. In previous videos, we have talked about reaction order, and we said that the reaction order is essentially the exponent above a particular concentration. The square brackets, again, are our indication that this is the concentration of component A. The superscript is the order. There are a variety of different orders that we will commonly see. While the order of a reaction can be any value, positive, negative, or fraction, more commonly there are three primary orders that you will see most of the time. There are zero order, which are somewhat rare, first order, which are common, and second order, which are very common. Zero order reactions are ones in which the superscript on the A is a 0. Anything raised to the 0 power is a 1, and so our change in the concentration, if this is our reaction, A goes to products, we would be measuring the rate in terms of our change in concentration of A. Because A itself is a reactant, it will be going down in concentration, and so the relationship between the concentration of A and the reaction rate is that the change in concentration of A is the negative of the reaction rate. So we would need the negative here to make them equal to each other. So our reaction rate is equal to essentially our rate constant. What this means is that if we're varying the concentration of A, it's not going to have any effect on how fast the reaction occurs. So some reactions or some processes that you will encounter that are zero order reactions are photolysis reactions. The reason why these are zero order is it's really how many photons are coming in and reacting with your species, not necessarily the concentration of your species. A lot of surface catalyzed decomposition, which you have your component binding to a surface and it breaks down catalytically. And so what's really causing the reaction to be a particular rate is how many surface sites there are for binding. So it's not the concentration of your solution, it's really how well is the surface at binding to the component that is reacting. First order reactions are fairly common. Radioactive decay, all radioactive decay of any radioactive material is a first order process. So carbon-14 decomposition is radioactive decay. Any unimolecular decomposition, of which there are many, is a first order process. Essentially, it is something that the more you have, the faster it breaks down. So for these processes, the order here, the exponent on our concentration is a 1, and that gives us a first order process. Second order, there's two types of second order processes that we would typically run into, although for our purpose, we're only going to consider the first. Second order are when two different things come together. So we have A reacting with another A to form the products. In this case, the exponent here is a 2, so this is the concentration raised to the second power. Another type of second order process would be A reacting with B, in which the rate of our reaction is equal to K times A to the first times B to the first, and so the overall order is 1 plus 1, or 2, giving us a second order reaction. The vast majority of reactions are second order reactions. When we're talking about integrated rate laws, however, we're only going to be really considering the first type, where it's A raised to the second power. Working with integrated rate laws for this other term are much more difficult and something that you would do in a more advanced chemistry class. Integrated rate laws are the integral of our rate laws. What we will be doing is taking a general equation, this one here, right, which relates concentration to our rate law. Note in this case I've moved the negative from in front of our change in concentration of our reactant to the other side. And then what we will be doing is taking the integral of both sides after a little bit of rearrangement. In the next slide, we will go through the examples of how to derive the integrated rate laws from our non-integrated rate laws, from the rate laws that we've been using up till this point. Now, because calculus is not a prerequisite for this class, you will not need to be able to do these derivations yourself. However, I do think it is important to have an understanding of where they come from, so sort of opening up the black box so that you can see what is going on, where they come from, so it's not just some mysterious equation. We will now work through how to derive the integrated rate laws for a zero, first, and second order process. In each case, we can start with our expression, negative D concentration of A dt is equal to K times the concentration of A raised to the power that we're looking at. So in the case of a zero order, it's a 0. In the case of a first order, we would have negative dA dt is equal to K A raised to the first power. I'm going to put a 1 there just so we can keep track of it. And then for a second, negative dA dt is equal to K A to the second power. Okay, so in order to do this, we need to get all of our A terms on one side and all of our T terms on the other. While I'm doing this, I'm also going to move the negative side from the left-hand side to the right-hand side. So I'm going to take my A, move that to the other side, move the negative sign in front, and I'm going to take my T and move it over here. All right? So that gives me change in concentration of A over A raised to the 0 is equal to minus K dt. I'm going to do the same thing for the first order. So that would be D concentration of A over concentration of A to the first power is equal to minus K dt. For the second order, D concentration of A, so our change in concentration of A over the concentration of A squared is equal to minus K dt. Okay, so we have these deltas. We need to get rid of that. The way that we do that is take the integral. So we're going to take the integral of each one of these expressions from our initial concentration, which is our concentration initially, A naught, to our concentration of A at time t. Concentration of A naught to upper limit of concentration of A at time t. Again, because calculus is not a prerequisite for the class, you don't actually need to know how to do the calculus. It's just showing you that it's possible to come up with these equations. So we take the integral to get rid of the dA. We also want to get rid of the dt. Now k is a constant, and so it can go outside the integral sign. And so we'll take the integral here from t is equal to 0 to whatever time we're interested in. We'll take the integral here from 0 to t, and take the integral here from 0 to t. Okay. So a raised to the first power is 1. So this is essentially dA, or the integral of dA, which is a. So we're going to have a at time t minus a naught is equal minus k, and then times what we get here, which would be t minus 0. For our first order, we have a raised to essentially the negative first power. or 1 over a. We're taking the integral of 1 over a. The integral of 1 over a is the natural log. So this would be the natural log of our concentration of a at time t minus the natural log of our concentration of a initial, a naught, is equal to the same thing that we had here when we were looking at the zero order. We can actually simplify that to give us minus kt, right? Because if we distribute the negative k into our values, right, we have this minus kt plus k times 0, which is 0. Okay, so for this one, for our last one, our second order, we're taking the integral of a raised to the negative 2, or 1 over a squared. The integral of that is going to be a to the negative 1, or negative a to the negative 1. So that would be negative 1 over a at time t minus negative 1 over a naught is equal to minus kt. Okay, we can take this and rearrange it. Well, first, there are a bunch of different ways of expressing the integrated rate law. One is the way that we have it here. So for our zero order, sometimes you'll see these as a at time t minus a naught is equal to minus kt. Then another form for the first order would be this one. This is a form that you will sometimes see it in, right? So here is one of the forms. And here we actually have, for the second order, we have a negative in front of a bunch of stuff, right? And so we could multiply both sides by negative 1, and the negatives are going to cancel out. Right, so that leaves us 1 over a at time t minus 1 over a naught equals kt. So I'm going to erase those to make it a little clearer. There. So this last one is another expression that we might see for the integrated rate law for a second order process. Now, a lot of times these end up getting used graphically, and so it would be handy to have these in the form of a y equals mx plus b. Now, our a naught is a constant. Once you start your reaction off with a particular initial concentration, you can't change the initial concentration. So this one is actually a constant, so we can move it to the other side. The a at time t is our dependent variable, right? The concentration of a at time t is dependent on how long you let the reaction go. So what we can do is move our a naught over to the other side, and that will give us a linearized expression. So this gives us a at time t is equal, we would add a naught to both sides, so this would be minus kt plus concentration of a naught. This is our y equals mx plus b. So our y is our concentration of a at time t. Our slope is minus k, and the intercept is a naught. So long as we're plotting concentration versus time, right? Time is our x variable. We would get a straight line if it is zero order. For our first order, there's actually a bunch of different ways that you're going to see this expressed. First, let's look at linearizing it, much like we did before. So a naught is still a constant once you let the reaction start. So we can move it to the other side, giving us natural log of the concentration of a at time t is equal to minus kt plus ln of a naught. So this gives us another y equals mx plus b. This is our y, that's our mx plus b. where our y is the natural log of a at time t. Again, our slope is minus k, x is our t, and b is the natural log of a. So if we plot this, looking at the natural log of our concentration versus time, we would get a straight line for a first order process. We'll finish it off with a second order, and then we'll look at some of the other mathematical manipulations that get done with a first order. So for a second order, a naught is again a constant, so we move it to the other side. 1 over a at time t is equal to, this time it's kt, not minus kt, plus 1 over concentration of a naught. This is y equals mx plus b. So y, our dependent variable, is a at time t, or 1 over a at time t. Our slope this time is k, not negative k. And our x is, again, time. Then our intercept would be 1 over the concentration of a naught. Because it follows that y equals mx plus b format, as long as we plot on the y-axis 1 over concentration, and on the x-axis time, we'll get a straight line if it's the second order process. Now, this second expression is another form that you will see the integrated rate laws presented in. The two expressions are equivalent. It's just a little bit of algebra has been done for the second one. So depending on where you look, you might see it in one of those two fashions. Now, going back to our first order, there's a rule for natural logs, which is the natural log of a minus the natural log of b is equal to the natural log of a over b. So a lot of times the first order reactions can also be expressed in terms of the relative concentration. So if we take the natural log of a at time t, our value here, and we're subtracting it from the natural log of a naught, using our rule for our natural logs, we can also express the integrated rate law for a first order process as the natural log of the concentration of a at time t over the concentration of a naught is equal to minus kt. Now there's an additional way of doing these, and I'm going to put it down here under my sort of second order. Okay, now there's another rule for natural logs, which is the natural log of a over b is equal to the negative of the natural log of b over a. When you inverse the ratio, you can move a negative sign in front. So another thing that gets done with this sometimes is we can flip our ratio up top, right? And if we flip the ratio, we can get rid of this negative sign. So another additional way that this can get written is the natural log of our concentration of a naught over concentration of a at time t is equal to kt. So I've flipped the ratio and I got rid of the negative sign. So for our first order process, there are a bunch of different ways of representing how things change with time. Okay, but the primary things we're talking about when we're talking about integrated rate law are the first ones that we came up with. Those are the prime examples of integrated rate laws. Now that we have those integrated rate laws, we can use the linearized ones, the ones where we were trying to make it equal to y equals mx plus b, right? The ones that we find here are 0, first, and second order, and look to see what happens when we do them graphically. So we had said that for a zero order process, if we graph the concentration versus time, we should get a straight line. So what I've done here is I have three different graphs, graphing it first as concentration versus time. The data that is presented with a red line and red squares is 0th order data. So that would be data from a reaction that is a 0 order process. The blue circle and blue line comes from data that it follows a first order process. The green circle with a dashed green line comes from a second order process data. So if we take data that is 0th order and graph it, concentration versus time, we get a straight line. If we take first order data, stuff that's actually first order, and graph it, concentration versus time, because that's not the correct linear equation for our first order process, right? First order should be natural log. What we find is that it actually has a curve. So because it has a curve, that tells us that this data is not a 0th order reaction. Similarly, second order also has a curve. Now the trick when you're doing this experimentally is you need to collect enough data so that you can actually see a curve. If we only look at the first 2 or 3 data points, they're all going to end up looking linear. You need to collect sufficient data that you'll be able to see a curve. For looking at it as though it was a first order process, that would be graphing natural log of our concentration versus time. Again, the red square with lightly dashed lines is 0th order, blue circle, blue line is first order, green circle, green dashed line is second order. You can see that if we plot 0th order values, 0th order data, on what would give us a line for a first order process, right, natural log versus time, it is curved. Because it is curved, we know that the data from the red line is not first order. The first order process, the blue line, is actually fairly straight. In fact, it is perfectly straight. The green data from the second order might appear at the beginning to look straight, but if you collect enough data, you'll see that it is clearly curved. Finally, if we graph all of our values, 1 over concentration versus time, this is what should give a straight line for a second order process. What we will see is that for a 0 order process, we have a curve. For a first order process, we also have a curve. And for a second order process, we have a straight line. So what this means is if you have a lot of concentration versus time data, you can mathematically manipulate the concentration to take the natural log of it, take 1 over the concentration, or just take the straight concentration, plot them all against time, and whichever one is a straight line will tell you whether it is a 0, first, or second order. If concentration versus time gives you a straight line, it's 0th order. If natural log of concentration versus time gives you a straight line, then it is first order. And finally, if 1 over concentration versus time gives you a straight line, then it is second order. Now, we can also do some additional things with these graphs. So if we look at the data on the appropriate graphs, such as the 0th order values being plotted on concentration versus time, which gives a straight line. The first order data are blue circles with solid blue line being plotted on the natural log versus time, and our second order data being plotted on what should give a straight line for a second order, which is 1 over concentration versus time. We can actually pull out some additional data from our graphs, right? Because our equations follow the y equals mx plus b format, the y value is our concentration versus time, natural log of concentration versus time, or 1 over concentration versus time. The m value in y equals mx plus b is the slope, and in the first 2 cases, the slope is equal to minus k. In the last case, in the case of a second order process, the slope is equal to k. Right? So for a 0th order, we get a negative slope. The k value has to be positive, and so the negative k is equal to our slope. Same with a first order process. We can figure out our initial concentration by going back to the y-axis and looking for where it intercepts. So our intercept, our b value, in the case of a 0th order process is a0. In the case of a first order process, it would be natural log of a0. And in the second order process, it would be 1 over a0. So what you can actually do is, given a graph, figure out what the initial concentration was. You will need to find out what the intercept was, and then in the case of a second and first order, do a quick back calculation, right, to get back your A naught value. So for a first order process, to undo the natural log, you'd have to raise the value for your intercept, e raised to that power. And then to undo a 1 over the concentration, you would take the reciprocal, or take 1 divided by the value for your intercept, would get you back the A naught value. We can know what the K value is by just looking at the slope and multiplying it by -1 in the case of a 0th order or first order process, and just taking it as is for a second order process. So this is one of the ways that in lab is commonly done to figure out the K value for a particular reaction.